and welcome. My name is Josh Thomas, and today my partner Matt Davey and I will be discussing Faraday's Law. We will demonstrate the application of Faraday's Law through an electrical generator. This project is for the summer 2013 session of MAE ECE 535 at North Carolina State University. Electricity is a staple component of our modern society. To make electrical energy, one could take mechanical energy and convert it to electricity. That is what we will demonstrate today. We will show by using a motor operating around 2,000 RPMs, we can generate electricity. First off, let's discuss how this is even possible. Thanks to a British scientist named Michael Faraday, we have Faraday's Law. Faraday's Law simply states that any change in the magnetic environment will produce a voltage. In the experiment we are about to show, we have a magnet moving in and out of a coil. The changing magnetic field induces a voltage in the coil. With a magnet moving through the coil and back again, an induced voltage is positive, then negative, and when the magnet moves back again, it's positive again. This movement results in an AC voltage. With the simple theory out of the way, let me turn it over to Matt to show you the actual system and how it works. Matt, take it away.
Thank you, Josh. Hello, my name is Matt Davey, and I will be demonstrating our voltage generator. In our case, the magnetic environment that we will be changing is the position and direction of the magnetic field or magnets relative to a coil of wire. Now first off, let's define a few terms. What is magnetic flux? Magnetic flux is the dot product of a magnetic field to a given area. Now EMF. EMF is the voltage induced in a circuit by a changing magnetic flux. Now Faraday's law states that the magnitude of the voltage induced in a circuit is directly proportional to the time rate of change of the magnetic flux across that circuit. In our case, our circuit is a coil of wire, two magnets, a diode rectifier, capacitor, and an LED. Now, as the magnets rotate and pass through the coil of wire, they induce a voltage in the positive clockwise direction. As they continue to rotate, they rotate out of the coil, and the magnetic field that the coil sees diminishes and reaches zero when the magnets are normal to the plane of the coil. As the magnets continue to rotate back into the coil, they now induce a voltage in the positive counterclockwise direction. Now, as Faraday's law states, the magnitude of this voltage is directly proportional to how fast I crank this handle, or how fast the magnets pass through this coil. So the faster I crank this handle, the higher the voltage the coil will produce, and the brighter our LED will be. Now if we go over to the oscilloscope, we can see the back and forth sinusoidal action of the voltage induced by passing the magnets through this coil of wire. In this case, the purple line will be the output from the coil, and the yellow line will be the smooth voltage coming out of the diode rectifier. If I crank faster, according to Faraday's law, the amplitude of the voltage seen increases, and that can be shown on the oscilloscope. A curious note is that the LED places a load on our voltage generator, reducing the overall output voltage that we see on our oscilloscope. So if I crank the handle, I can see that I get a peak-to-peak voltage of roughly 6 volts. If I remove the diode from the circuit, continue to crank our generator, now our peak-to-peak voltage is roughly 12 to 13 volts. You can see how the LED and resistor place a load on our circuit.